Okay, so today we're going to pick a problem from the AP exam in statistics. It's 2015, number 5. And this was a two-sample t-test. What you're doing in this problem is you're comparing the mean of one population to the mean of another. So let's just take a minute to look it over. There's these two stores. One's called Buy Right Pets and one's called Fish Friends. And several managers at the pet store suspect that the lengths of fish from Fish Friends are consistently bigger. So that's the belief that maybe the numbers here, we look at the Fish Friend numbers and underlined in red and compare them to the Buy Right numbers, these lengths. It looks like the mean for the Buy Right pets at 3.40 is slightly less than the mean of 3.46. So then this innocent little question comes along. It says, do the data provide convincing evidence that the mean length of adult fish from Fish Friends is greater than the fish from Buy Right? And whenever you see that language, do the data provide convincing evidence? I'm putting stars next to it. That means you have to do a significance test. So every significance test, you always have some things you need to do. You need to start by creating some hypotheses. So it looks like they're using N sub B for Buy Right Pets and N sub F for Fish Friends. So let's start to write this problem out. This will take a little while. Okay, so I'm going to start by saying let mu sub F equal the mean length of fish from Fish Friends, which is the one store, and then mu sub B equal the mean length of fish from Buy Right. And then your hypotheses are, well, based on what they said in the problem, the manager suspected that Fish Friends had bigger fish. So usually when you write your null hypothesis, you try and indicate that there's no difference, that one's not better than the other. We would write that by saying that the mean for Fish Friends minus the mean for Buy Right was equal to 0. And HA, the alternative hypothesis, is usually what you suspect is true based on observation or something. And in this case, the suspicion is that the mean length of fish from Fish Friends is bigger than the mean length of fish from Buy Right, which means this difference would be greater than 0. So that's always how you start these problems off. You start by writing your hypotheses, and then we go from there. Okay, now before you do a test, you always have to check your assumptions. Usually we first want to check that SRSs were done. So we need to state that they were both SRSs. In other words, the fish from Fish Friends store and the fish from Buy Right's store were both picked randomly, and that there's no careful selection of the sample. All right, the second thing you always want to check for is independence. Now you're going to need to check that twice here. We need to check that the population of fish from Fish Friends is greater than or equal to 10 times the sample size of fish from Fish Friends. So we look at the problem here. It looks like we had 10 fish from Fish Friends. We can see that here, NF equals 10, and we had 8 fish from Buy Right. So what we really want to say here is that the population of fish at the Fish Friends store should be greater than 10 times 10 or 100. So we're going to have to assume that because we weren't told how many fish are in that store. Okay, so we know that when you do this, that allows you to make sure you can, well, let you know that you can use your standard deviation formula. So our S of X bar for Fish Friends would be S of X for Fish Friends over the square root of N for Fish Friends. We know we had 10 fish from there. We need to get the standard deviation of this sample. And the only way we're going to do that is by putting the data into the calculator. So let me do that for you and tell you what you would get. Actually, before I go typing that in the calculator, I think we go back to the problem. They even told us, oh, there it is, look, 0.55. So I can just put this 0.55 here. Now I should figure out what this is. So let's do that. So 0.55 divided by the square root of 10, and we get around 0.174. Okay, you need to do the same thing now again for the buy right store. So we need to show that the population, or at least assume that the population of fish at buy right pets is greater than 10 times the sample size of fish that we're taking at buy right pets. Well, that would be 10 times 8, or 80. So we need to assume that the store has more than 80 fish in it. And if that's true, then we know the standard deviation of X bar for Best Buy is the standard deviation of X for Best Buy over the square root of the sample size for Best Buy, or buy right, I think. I think I'm getting confused with the store. If we look up top, looks like that standard deviation is 0.434. So they were nice enough to give that to us. So we could put 0.434 here over the square root of 8. And if you take the time to divide that, 0.434 divided by the square root of 8, we get around 0.153. Interestingly, in this problem, we're not actually interested in these two separate standard deviations. What we're really interested in is the standard deviation of the difference. And you know that from your hypotheses. The variable of interest is this, QF minus mu B. And so if we want the standard deviation of a difference in two random variables, then we learned in a previous video that you can never add or subtract standard deviations. You can only add variances if the two variables are independent. There's no reason to think that the size of the fish at Fish Friends has any effect on the size of fish at Buy Right, and they're getting the fish from different suppliers, so we can say they're independent. So what we really care about here is the standard deviation of X bar of Fish Friends minus Buy Right. So that's F minus B, and that's going to be, we take our two variances, so you square these standard deviations, and then we take the square root. And if you take the time to do that, you get about looks like it's about 0.232. So that's a lot of work, but this is the extra step when you go to two samples. You have two sets of assumptions to essentially check, and then you need to combine them to make this standard deviation that you really want. Okay, so the last check is for normality, or is it safe to use the t-test? And ideally, you would have wanted n to be, n for Fish Friends to be greater than or equal to 30, n for Buy Right to be greater than or equal to 30. Fortunately, neither one of those things happened. I think n for Fish Friends is 10, and n for Buy Right is 8. So what you need to do in both of these cases is create box plots and see what they look like. Or you can do what is called a normal probability plot and hope that they're linear. So if you have a T84, that's a good way to. So in the case of Buy Right, the box plot looks something like this. It's a slightly smaller tail on the right. So we would say that this is moderately skewed. It's not strongly skewed, and there's no outliers. So this is safe to use. If we take the time to compute the box plot for the other one, this box plot really couldn't be any nicer. It's got slightly longer tails than the other one. But wow, it's almost perfectly symmetric. So that means it's safe to proceed. So since both of these box plots are either symmetric or close to symmetric, there's no outliers present, it's safe to use the t-test, which means it's time to move on to our picture. So let's draw a picture of our normal distribution, our normal-esque distribution. Remember, t-distributions really aren't normal distributions. They look like normal distributions, but they're slightly wider. Remember, when you talk about a t-distribution, one of the things you care about is something called degrees of freedom. Now, that'd be a little confusing here. Typically, in the past, degrees of freedom is always n minus 1, but that's for a one-sample test. And today we have a two-sample test. So what you do is degrees of freedom equals the minimum of n Fish Friends minus 1 and n Buy Right minus 1. So in our case, the degrees of freedom would be the minimum of whatever 10 minus 1 is, and 8 minus 1, or the minimum of 9 and 7, so you would just get 7 for an answer. And that's sort of just like playing it safe. You just go with the smaller degrees of freedom to be safe. Okay, in the middle, we always put HO, which in this case is 0. That's our HO. And our standard deviation of X bar fish friends minus buy right was 0.232. So if you want, you can mark those off. So here's 0.232, here's 0.464, and then going the other way, negative 0.232 and negative 0.464. So there you have it. Now the final thing we need is we need to know what the difference in the X bars were. So we need X bar fish friends minus X bar buy right. Now luckily in the problem they gave us those things. X bar fish friends was 3.46 and X bar buy right was 3.4. So this would be 3.46 minus 3.4. And if we subtract that, we get 3.4, sorry, you get 0.06, which you'll notice is not far away from 0 here. It's only about there. And then the area we want is got to be greater than that. So, because our HA is that we thought mean was going to be greater. So we're going to have a really big p-value here, and we're not going to end up rejecting H. So the area of this region up here ends up being about 0.4, which is really big. So what does that mean? The typical alpha level used for one of these problems is 0.05. Our p-value is 0.4, which is definitely greater than alpha equals 0.05. So we would say we fail to reject HO. We can say our test was not significant. We can say that we did not find any evidence to support the claim that the fish from Fish Friends were actually bigger than the fish from Buy Right. And so what you've learned today is basically that when you have two means from two different populations and you want to compare them, you have to use something called a two-sample t-test. And in essence, it's just like any other significance test. You start off by writing your let statements and hypotheses. You check your assumptions, you compute your standard deviations. You really should make note of your X bars while you do it. The tricky part here is that when you get your two separate standard deviations, you have to realize that you want to combine them into one by adding the variances. So that's super important. And then we go draw our distribution with HO in the middle of 0. We mark off the difference in our sample means, which turns out to be really small here. And because of this standard deviation, the standard deviation is 0.23. 0.06 is not even one standard deviation away from the mean. So we end up with a very large p-value of 0.4, which is about as big as it gets. So these people were really off base in saying that they thought the fish were bigger from one store compared to the other. Okay, that's it. Hope you enjoyed watching.